Hi, everyone. Today we are going to study about traveling microscope. Actually, we have many instruments in the syllabus. We know normally we are using meter ruler. We use meter ruler to measure lengths more than 10 centimeters. And it is sufficient to measure any length more than 10 centimeters. If you want to measure in between 10 centimeters to 2.5 centimeters, you can use vernier caliper. But if the reading is in between 0 and 2.5 centimeters, we can use more accurate instrument, uh, micrometer screw gauge. And here, uh, traveling microscope we use to measure internal diameter of a capillary tube. We don't have other instrument in the lab to measure internal diameter of a capillary tube. Then here least count of this traveling microscope is 0.01 millimeters. I'll explain after this main part how to calculate least count. And we can measure diameter of a rubber tube also. Actually, we can use traveling microscope to measure internal diameter of a capillary tube because we don't have other instrument to find internal diameter of a capillary tube because we can't put those jaws into the capillary tube. Therefore, definitely we need these instruments to measure internal diameter of a capillary tube. And also rubber tube. Diameter of a rubber tube we can't measure using using vernier caliper or micrometer screw gauge because it will deform. When it is placed in between the jaws, it will deform. Therefore, we have to use this traveling microscope to measure diameter of a capillary tube and diameter of a rubber tube. First, we have to study parts of this traveling microscope and uses of them one by one. I gave you here diagram of traveling microscope. First, we have to study parts of that and requirement of them. Then here you can see A. Two screws are there. They are known as leveling screws. At very first, this platform should be made horizontal exactly. Otherwise, this traveling microscope can't move vertically exactly and horizontally exactly. Then first we have to level this. To level this, we can use these tilting screws, that means leveling screws A, and here you can see spirit level. Until this air bubble in the spirit level comes to the midpoint, we have to rotate leveling screws. Then exactly this platform is horizontal. After that, you should know about C. Actually, you have horizontal vernier here, horizontal main scale here. In the horizontal main scale, maximum range 22 centimeters. Vertical main scale, it has maximum range 17 centimeters. Here it has a vernier, two verniers are there. Horizontal vernier of the traveling microscope. This is the vertical vernier of the traveling microscope. Two verniers, horizontal vernier and vertical vernier. Then there is a locking screw. Is the locking screw. Then if you want to move this traveling microscope slowly, right, to move it slowly, we can use this fine adjusting screw. C is known as fine adjusting screw of the horizontal vernier. When it is rotated, this traveling microscope will move horizontally very slowly. Fine adjusting screw of the horizontal vernier. And you should know this also. It works when this screw is tightened. There's another screw here, right, which is connected to the vernier. Before using that fine adjusting screw, we have to tighten this screw E. That is the tightening screw. Then when it is tightened, this works. That means fine adjusting screw works. Using fine adjusting screw, we can move this very slowly in the horizontal direction. And there's another one here, vertical fine adjusting screw. When it is rotated, this vernier can be moved vertically very slowly. Then to do that, you have to tighten this screw. There's a tightening screw of the vertical vernier. Q, tightening screw of the vertical vernier. When it is tightened, this fine adjusting screw will work. And this is a traveling microscope. It has main parts. First one, eyepiece. 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 J is known as eyepiece. This one, objective lens. Objective lens. K is here. Objective lens. This is the focusing screw. When this focusing screw is rotated, entire traveling microscope goes up and down, up and down. This microscope is going up and down when the focusing screw is rotated. And here, least count of this instrument, 0.01 millimeters. Therefore, distance between two consecutive lines will be very small. When you are taking readings, it is hard to find the correct coincide line. To take those readings sharply, we use here magnifying glass. This is the magnifying glass of the horizontal vernier. This is the magnifying glass of the vertical vernier. And another parts you should know, there's another lever here. You can see a little bit long rod, K. It is known as releasing lever of the microscope. When it is released, right, if you want to tighten it, it should be rotated clockwise. If you want to release that, you have to rotate it in the counterclockwise direction. Then microscope will be released and you can rotate it. After that, you can rotate this microscope. Then these are the main points of the traveling microscope. In the main scale, direct least count 0.5 millimeters. But in the vernier, vernier has equal 50 divisions. With that, its least count 0.01. Then in the instrument also, you can see those points. Here, I'm going to explain that also. Then you can see these are leveling screws. By rotating them, this should be made horizontal exactly. There's a spirit level here. Using the spirit level, then we have to rotate those screws until that air bubble comes to exactly midpoint of the spirit level. And here horizontal main scale has 22 centimeters maximum range. And this is the magnifying glass of the horizontal vernier. This is the locking screw of the horizontal vernier. When it is tightened, this fine adjusting screw works. And this is the vertical vernier here. There's a locking screw. Actually, it is located in the back side of this. This is a locking screw of the vertical vernier. When it's locked, this works. Then this is the fine adjusting screw of the vertical vernier. This is the microscope. This is eyepiece. This is objective lens. This is a focusing screw. When it is rotated, entire microscope is going up and down. And this is the releasing screw of the traveling microscope. When it is released, you can rotate this in any direction. Right. These are the main parts. Then this is a horizontal fine adjusting screw. They work when screw in the vernier scale is tightened. Then first we are going to study how to find internal diameter of a capillary tube. Then I'm going to draw it here. You can see we need stand for that, right? This is the capillary tube. We want to measure internal diameter clearly. To find that, first this should be placed on a supporter. After that, this travelling microscope should be made horizontal. This should be made horizontal, you know. Then you have to release this releasing lever, and it should be made horizontal. Then travelling microscope should be placed in front of this. Actually, before taking readings, you can see inside of this travelling microscope, cross wires are there, cross wires. Then at very first, move the eyepiece only. Move the eyepiece until you see a sharp image of the cross wires. Move the eyepiece here while seeing through this until you see a very sharp image of cross wires. After that, don't move it again during the experiment. And then first we have to focus this to the tube. Then you have to use focusing screw. This focusing screw I, it is here. Then rotate focusing screw slowly until you see a sharp image of this capillary tube. Focusing screw we have to rotate until you see a sharp image of that tube. After, how do you move that? Using the focusing screw, forward and backwards. It can be moved. And after that, we are taking vertical diameter and horizontal diameter both. Then to measure the vertical diameter, we have to move this travelling microscope from here to here. From here to here, we have to move this travelling microscope. Then to move it in the vertical direction, we have to use this fine adjusting screw of the vertical vernier. Then rotate that until this cross wires exactly comes to the upper edge. Then you can see, when seen through the microscope, you can see this way. Until horizontal wire exactly touches the upper edge of the circle. You have to rotate this fine adjusting screw, this one. After that, take the reading shown by the vernier. Take the reading shown by the vernier. Take the reading shown by the vernier. I can take it Y1. After that, this should be moved down. It should be moved down until you see this bottom edge of the circle as the same. Then how do you move that? Then you have to rotate this one again in the clockwise direction to move the travelling microscope down slowly until it comes to lowest edge of the circle. Then you can see cross wires are coming to here. And take the corresponding reading Y2. Then when you are taking vertical readings, what you have to do? You have to rotate this fine adjusting screw, vertical one. Before rotating that one, you must be mindful, this screw should be tightened, otherwise this will not work. Then we took two readings vertically, Y1 and Y2. Now you can measure vertical internal diameter of the tube. Vertical diameter I can write here, vertically equals y1 and y2 difference. If y1 greater, y1 minus y2. If y2 greater, y2 minus y1. Then using difference of them, y1, y2 difference divided by 2 is equal to radius of the capillary tube. Then we took this from the vertical vernier. Now you should know this also. If it is not made horizontal, then you can see this wire exactly will not go vertically. Then one reading will be here, another reading will be here. It goes in an inclined direction. That's why I told you at the very first, this travelling microscope should be made horizontal before taking the readings. Otherwise, exactly you can't take upper edge and lower edge readings. Then we found vertical diameter and vertical direction radius. And now we have to take horizontal diameter. Then to take horizontal diameter, you have to move this microscope in the horizontal direction. Then to the right edge and left edge. Then to do that, you have to use this fine adjusting screw C. Fine adjusting screw C. Then you can move it this way and this way in the horizontal direction. Then take first reading. Before taking that one, I told you, you should be mindful. This should be tightened. This should be tightened. Otherwise, fine adjusting screw will not work. Then take first reading when vertical and horizontal wires comes to this edge like this. X1, cross wires are here. After that, again rotate that fine adjusting screw until microscope comes to the left edge. Then you can take this reading here, exactly x2. Now we can measure horizontal diameter. Horizontal diameter you can measure dx. x1, x2 difference, that is diameter here to here, divided by 2 radius. This is diameter in the horizontal direction. Then we have 2 values for the radius. Here R1, here R2. Then R1 plus R2 over 2 gives a best value for radius of the tube. And we can measure horizontal diameter dx. It should be divided by 2 to find the radius in the horizontal direction. If you want to measure this diameter very accurately, take many readings and calculate an average value. When you are taking many readings and calculating average value, that human error, that means a random error, can be reduced. Now we are going to find internal and external thickness of a rubber tube. External diameter we can find, internal diameter we can find, and thickness of a rubber tube. Same way we have to do that also. I am going to explain again. If you are given a rubber tube, then you have to take another reading to find the thickness. Then you have to take here, if it is a rubber tube, previous one I did for glass capillary tube. Now I am going to do this for rubber tube. Then if you use a rubber tube, as the same you have to take vertically internal diameter and horizontally diameter, internal diameter, and you need another 4 readings for the edges of the tube also. Then again you have to move this microscope vertically to focus it at this edge. Then you can take again y1 dash and move the microscope down until that horizontal wire and vertical wire comes to the lower edge of the tube. Take next reading y2. Then you can measure external diameter of the rubber tube. Internal diameter we know, y1, y2 difference, external diameter y1 dash, y2 dash difference. Then you can measure thickness of the rubber tube. Then how do you find that? y1 minus y2 divided by 2 external diameter. y1 minus y2 internal diameter. Difference of them is equal to this thickness plus this thickness. It should be divided by 2 to find the thickness of the rubber tube. This is what we are doing with this traveling microscope. Then sometimes in practically, if you want to find diameter for the entire tube, if you want to find diameter for the entire tube, not only edges. Here we found at the edge of the tube internal diameter, external diameter. But if you want to measure a diameter, average diameter for the entire tube, there's another method that is normally we are not doing in the lab because we have to use mercury. Now normally we are not using mercury in the lab. But there's another method like that also if you want to measure diameter for the entire tube. Then we have to add a small mercury thread into the tube. A small mercury thread into the tube. Actually you can see it here. There's a capillary tube with a mercury pellet. Normally we are taking 150 millimeters mercury pellet into the tube. After that, we have little bit different methods to calculate diameter, average diameter for the entire tube. I'm going to explain that also. Now, a mercury pellet should be inserted into the tube. Normally length should be 150 millimeters. It should be inserted into the tube, capillary tube. After that, we are measuring length of the mercury pellet when it is located at different 3 points, 3 locations inside of the tube, like this. We can measure length of this mercury pellet. To measure length of that mercury pellet, tube should be placed on this platform. Here you can see there's a platform here. This tube can be placed on this. After that, we can measure horizontally length of the tube. To measure that length of the tube, microscope should be made vertical again by the releasing lever. It should be made vertical and take readings at these 2 edges. When cross wires are coming to here, we can take first reading, and here also we can take another reading. But here you can see we have to drag this microscope in a long distance. Then actually we are not using here fine adjusting screw. Then release this tightening screw, you can drag it from here to here and take the first reading. After that, this should be released again. This should be dragged this way. After that, tight that one, it should be tightened, and for the fine focusing. After that, you can take here reading also, then x1 and x2. Then you can measure length L1 here to here by the difference of x1 and x2. Do the same procedure when mercury pellet little bit moves this way or any direction. The next reading we are taking when mercury pellet comes to somewhere here. Again take readings at two edges of the mercury pellet. Then cross wire should touch this exactly like this. Vertical wire should touch at the edge of the meniscus of the mercury pellet. Then take next readings x3 and x4. x3 here, this one x4. Then you can measure this length as L2. It is equal to difference of x3 and x4. x3 minus x4 or x4 minus x3 because we need only the magnitude of the length. Then again it should be taken to the left edge and do the same procedure to measure the length of the mercury pellet. Normally we are using here 150 millimeter long mercury pellet to minimize the fractional error. Then here vertical wire should come to the edge of the meniscus exactly. Vertical wire should come to the edge of the meniscus exactly. Then to do that, I told you in a long distance you have to move this microscope. Therefore, this should be released. Then you can drag it. After that, it should be tightened again. Then you can focus it exactly. Then take next two readings, x5 and x6. Then you can measure again length of the mercury pellet L3 by the difference of them x5 and x6, big one minus small one, x5 minus x6. Now next step, we can calculate average length for this. Average length, you know, why we are taking this kind of many readings? To minimize random error, to minimize human error. Then we can measure average value for the length of the mercury pellet. Here length L3, then you can measure average value L1 plus L2 plus L3 divided by 3. Then we have average length for the mercury pellet. And you know, 5r squared into length means, you know, volume of mercury pellet. It's a cylindrical mercury pellet. Then you know 5r squared, 5 22 upon 7, 5r squared into average length. 5r squared into average length is equal to volume of this mercury pellet. You know, density means mass over volume. Density equals mass over volume. Then density into volume is equal to mass. Then this volume can be multiplied by density of mercury. Density of mercury. We know density of mercury 13,600. This should be the mass of this mercury pellet. And this mass of the mercury pellet we can measure by the triple beam balance or quadruple beam balance. That means 4 beam balance. Exactly how do you measure that? First we are measuring mass of the tube and mercury together, M1. Mass of the mercury pellet and tube. First reading. First reading. After that, remove the mercury pellet and measure the mass of the empty tube using travelling microscope M2. Then you know difference of them is equal to mass of mercury. Then if you know mass of mercury, it is equal to phi r squared volume into density. Now you can subject r, that is very, very accurate value for the entire diameter. In some experiments, especially we are doing later under viscosity Poiseuille's method. For that method, we need average diameter for the entire tube. Then actually this method also very accurate method. Normally, this is we are not doing in the lab because now mercury is not in the lab, it's poison. But this method is very accurate anyway to measure diameter for the entire tube. Previous method we took only diameter at the edges. Now this one gives very accurate value for the entire radius of the tube. Then these are the basic parts of travelling microscope. Quickly I am going to explain this again. What are the parts here? Leveling screws A. Why we are using leveling screws? To make this horizontal exactly. How do you make this horizontal exactly? Rotate these two, actually two screws we can rotate only. Rotate these two until that air bubble in the spirit level comes to the midpoint. Then it is horizontal. If it is not exactly horizontal, this traveling microscope, this microscope can't move exactly vertically and horizontally. Then this should be made horizontal first. And I told you this is a horizontal main scale. It has maximum range normally 22 centimeters and least count of the main scale only 0.5 millimeters. Least count of the main scale only 0.5 millimeters. With the vernier, vernier has 50 divisions. Then least count of this vernier 0.01. We have magnifying glass. What is the purpose of magnifying glass? To take readings sharply. To take readings sharply or to minimize uncertainty error. Uncertainty means exact point we can't find if so many lines are there. Therefore, we can use this magnifying glass to take readings sharply. And you know, this is a tightening screw of the horizontal vernier, and when it is tightened, only this fine adjusting screw works. This fine adjusting screw works when this one is tightened only. And this is a vertical vernier, vertical locking screw of the vertical vernier. This is a microscope, objective lens, eyepiece, crosswires inside. This is the focusing screw, focusing screw. This is a releasing lever of the microscope. When it is released, this can be made horizontal, vertical, in direction you can rotate. This is the fine adjusting screw of the vertical vernier. This works when this one is tightened. This is the locking screw of the vertical vernier. These are the main parts of the travelling microscope. Then you should know how to find internal and external diameter, how to find thickness of a rubber tube, and this addition and extra part for this. This travelling microscope again we are using in the light lesson to measure, to determine refractive index of a transparent block. Not here for the moment, you can understand that. Therefore, I am going to explain now how do you calculate least count of a vernier scale. I am going to explain about vernier principle here. To minimize least count, we have this method. It's a very simple method. I gave here 1 centimeter length here to here, you know. 1 centimeter is very small value. I drew here enlarged one. Then first I am going to take a certain distance from the main scale. Certain distance from the main scale. For example, I am going to take here 9 millimeters. 9 millimeter length from this. 9 millimeter length I selected from the main scale, and it can be divided by number of divisions in the vernier. This is known as vernier scale. It can be moved related to the main scale. Then here vernier scale has 10 equal divisions. 10 equal divisions. Then you can find width of a division. Width of a division, I took 9 millimeters. It can be divided into 10 divisions. Then width of a division, I can draw here 0.9 millimeters. That is width of a division. Width of a division 0.9 millimeters. But we know length of this one division in the main scale 1 millimeter. Here to here 1 millimeter. Then new least count of the instrument. New least count, this small part. This small part is the new division, new least count. Then how do you find that? This 1 millimeter minus 0.9 millimeters. The difference is equal to 0.1 millimeters. Then least count of this new instrument 1 millimeter. This is the least count of the main scale minus width of a division. Width of a division 0.9 millimeters. Therefore, new least count actually 0.1 millimeters. This is the least count of the instrument. If this vernier scale shift until this first line coincides with this line, then distance travelled by the vernier related to the main scale is 0.1. If this division coincides with this, distance travelled by the vernier is equal to 0.2 millimeters, because here to here 2 millimeters, here to here 0.9, 0.9, 1.8, 2 millimeters minus 1.8 millimeters, 0.2 millimeters. That means we can measure multiples of 0.1 millimeters. Then we reduced here least count up to 0.1. Then what is the general equation for this? Then normally we can take least count of the main scale as simple A. It is not always 1 millimeters, it can be 0.5 millimeters, in the extended vernier it's 2 millimeters. Width of a division 1 millimeter. And length selected generally I can write L. And generally I can write this one, we took 0.9 millimeters divided by 10. In generally we can write this L over, that means length selected divided by number of divisions in the vernier. Now we found least count by the difference of least count of the main scale and width of a division. What is that difference? 1 millimeter minus 0.9, generally I can write 1 millimeter means A, least count of the main scale, A minus width of a division, it is L over N. L over N. Then this is the main equation for least count. Actually we have another short method for this. Short method this. If the number of divisions selected from the main scale and number of divisions in the vernier scale, right, difference of them is equal to 1. For example, 9 divided into 10 millimeters, or you can write 19 millimeters divided into 20 divisions, or 49 millimeters divided into 50 divisions, or 99 millimeters divided into 100 divisions. Then always difference 1. If difference is 1, you can use a short method, least count divided by number of divisions. This also least count, you can check it. Least count of the main scale 1 millimeters, length selected 9 millimeters, number of divisions selected 10 here. Then you can see here least count 1 minus 0.9, 0.1 millimeters. .1 millimeters. And short method also we can check least count of the main scale divided by number of divisions in the vernier. It's 10, therefore it is equal to 0.1 millimeters. Same answer. Then both methods are correct. Least count of the main scale, length selected, number of divisions, right? But as our need, we can reduce least count. Then you can take 19 millimeters from the main scale and 20 divisions in the vernier scale. Then 19 divided by 20, then you will see least count 0.05 millimeters. And you can take 49 millimeters from the main scale and 50 divisions for the vernier. Then 49 over 50, 1 minus 49 over 50, you will see least count 0.02. And you can take 99 millimeters can be divided into 100 divisions. Then 99 over 100, 0.99, 1 minus 0.99, 0.1. Then as our need, we can reduce least count. But there's a small problem. When you take so many divisions, it is hard to find coincide line exactly. If it is hard to find coincide line, you have to use this kind of magnifying glass or another method, that is circular scale method, to minimize this uncertainty error. Then in the vernier, we have, in the travelling microscope vernier, we have 24.5 millimeters in the main scale. In the normal microscope we have, I am going to explain that also. In the normal travelling microscope we have 0.5 millimeters least count of the main scale. In the main scale, here main scale least count 0.5 millimeters in the travelling microscope. And length selected from the main scale, this one 24.5 millimeters, L 24.5 millimeters, divided by number of divisions in the vernier. In this travelling microscope vernier has 50 equal divisions. Then you can find here least count 0.01 millimeters. 0.01 millimeters. And you can apply short method also. What is short method? Least count of the main scale, number of divisions, because 49 divisions divided into 50 divisions. Then short method 0.5 millimeters divided into 50 equal divisions, 0.01 millimeters. This is the least count of the travelling microscope. I told you when so many divisions are there, it is hard to find the coincide line. That's why we are using a magnifying glass in the travelling microscope. And sometimes to minimize this error, that means sometimes if so many lines are there, it is hard to find coincide line. No? Therefore, we can use another method. It is known as extended vernier principle. It's little bit difference compared with this method. Here I took 10 divisions. Instead of 10 divisions, we can take 5 divisions. I'm going to explain that also. Extended vernier principle. In this diagram, you can see 9 millimeters from here to here, 9 millimeters. But in the vernier, it has only 5 divisions. But in the vernier, it has only 5 divisions. Then, width of a division is equal to 9 millimeters divided by 5 divisions. It's 1.8 millimeters. What is the least count? I told you. Least count means minimum reading that can be taken. Then what is the minimum reading we can take here? This is the minimum reading. When this coincides with this, that value we can measure. It is equal to 2 millimeters minus 1.8 now. 2 millimeters minus 1.8. Least count here. 2 millimeters minus 1.8 millimeters, 0.2 millimeters. What is the relative advantage of this vernier? Its least count a little bit low, but compared with that, very, very easy to find the coincide line. If so many divisions are there, it is hard to find coincide line. Therefore, this principle can be used in the vernier, sometimes 19 millimeters divided into 10 divisions, 49 millimeters divided by into 25 divisions. That also we can do. But for that kind of questions, you have to increase A one by one until you get first positive answer. Right. Then I'm going to explain how to take a vernier reading. From a vernier scale, how do you take reading? I took here a small example. This is a vernier scale. You can see 10 divisions are there. If normally 10 divisions are there, as we did before, least count 0.1 millimeters. As we did before, least count 0.1 millimeters. Then how do you take readings from a vernier? First, find the line where just before the zero of the vernier. Find the line in the main scale where just before the zero of the vernier. Find the line in the main scale where just before the zero of the vernier. How much that value? 1.9 millimeters. Because here 2 centimeters, you can see this should be 1.9 centimeters, 1.9 centimeters, and here 1.9 centimeters. This is a direct reading. How do you find that? Find the line of the main scale where just before the zero of the vernier. We took that one. After that, you need this length. To find that, you can use vernier principle. You have to find coincide line. How many coincide divisions are there? You can see this is the coincide line. This is the coincide line. 1, 2, 3, 4, 5, 6, 7. 7 divisions. Coincide line, 7 divisions. That means when this is moved a distance, 7th division coincided that main scale value. Therefore, 1.9 centimeters plus 0.1 is the least count into 7 divisions. 0.1 millimeters is the least count into 7 divisions. Then you can see 1.9 centimeters plus 0.7 millimeters. Then you can see 1.9 centimeters plus 0.7 millimeters. To add them together, we have to convert this to centimeters. 0.07 centimeters. Therefore, reading here 1.97 centimeters. This is a reading. Then how do you take that? Always you have to use this method. What is that? Find the line where just before the zero of the vernier. Find the line in the main scale where just before the zero of the vernier. That value 1.9 centimeters. Not only that, this is the distance traveled by the vernier. You know, always when vernier travels, you can find that distance by the coincide line. As I did before, you can see But anyway, I can explain that also. Here 1, 2, 3, 4, 5, 6, 7. If seventh one goes from here to here, distance travelled by the vernier is equal to 7 into least count. 1, 2, 3, 4, 5, 6, 7. Seventh one coincides with this. Then distance travelled by the vernier, distance travelled by the 0 is 0.7 millimeters. That's why I took here 0.7, because 0 should shift a distance of 0.7 by 7th division coincide. Then reading 1.9 plus 0.7 millimeters. And you can find here fractional error. Fractional error means least count over reading. Least count here 0.1 millimeters. This is a least count. This is a least count divided by reading. Least count over reading is the fractional error. Reading 1.97 centimeters, but actually both should be in the same units to divide that. Therefore, I can write this 0.1 millimeters divided by 19.7 millimeters. That means fractional error 1 over 197. 197. Then this is how we use verniers to minimize the fractional error. I told you two methods are there. First method, we have to reduce least count in the main least count. Second method, we have to increase the reading, but I told you always we can't increase the reading. Therefore, least count should be reduced. How do you reduce least count? Many methods are there. First one, vernier method. Before that, if you want to do this method also, that main scale can be divided into more divisions. Next one, vernier scale principle. Next one, circular scale principle. Then circular scale principle we can study from the next lesson. These are the basic things we did. Then if you want to see these lessons again, then channel you can use YouTube NIE to watch these videos again. Then study this well. It's very simple principle. From the next video we can do circular scale principle. That is the next method to minimize least count, because here when number of divisions increases, it is hard to find uncertainty error is coming. We can minimize that also with the circular scale principle. Then thank you very much.